1.6, continuity. In everyday language, continuity means unbroken, has no holes. Continuity means unbroken, has no holes, and also no jumps. So no gaps, no jumps, no holes. So let's look at this example of a function that has lots of those things. It has holes and jumps. So it starts nicely. It has a hole over here. We have a jump and we can mark those points. The first point is C1. The second point is C2. So a jump here and then goes up another hole. But this hole, we say we redefined it by adding a filled in point here, and it continues here. So this point here is C3. So our function has three very important points to discuss. So we're gonna detect points of discontinuities here, detect or examine points of discontinuities. So looking at the graph from left to right, our first point is C1. What's happening at point C1? We have a hole geometrically, but mathematically means that f is not defined at that point at C1. In other words, C1 is not in the domain. That's why we have a hole. So we have discontinuity. The line is broken at that point. And for that reason, because the function is not defined at C1. The second point, C2, we see that this function is defined at C2 because we have this filled in circle. So the function is defined. However, the limit, I need to erase this part, here you go. The limit of the function at that point C2 does not exist because the right hand, the left hand are different. So we have this jump. So again, our function is not continuous at C2 because the limit at that point does not exist. And finally, at point C3, our function is defined at C3 because we have this filled in circle. The limit exists from the left and from the right. But the problem here is that the limit that exists when x approaching C3 is not the same as the value of the function at C3, because the value of the function at C3 is at that point, but the limit is over here. So we had three different reasons for which the function was discontinuous, and that would help us make the definition. We say f is continuous at some point C if three things are important. Number one, it has to be defined. F of C is defined. In other words, C has to be in the domain. Number two, the limit of f of x when x approaches C has to exist. So we saw when that was a problem for C2, we had discontinuity. We had that jump. And number three, these two, number one and two, have to equal to each other. In other words, the limit of f of x when x is approaching C has to be exactly f of C. So three important conditions for the function to be continuous. Now, what does it mean for a function to be continuous on an interval? Because that was just continuous at a point, this definition. So we say f is continuous on some interval from a to b if f is continuous at every point. At every point in the interval from a to b. So if you have to prove something on an interval, you pick a random point, call it x, and check all these three conditions for that random point. Now, here's a very important theorem that can help things. Part A, polynomial functions such as x, x squared, x to the third, and so on. So polynomial function is continuous everywhere. So think about the parabola, the line. You can trace the graph of these functions without lifting up your pen. So they have no jumps, no holes, no gaps. So if you see a polynomial function, you can say continuous everywhere. Now, rational function, that's like 1 over x, a ratio of two polynomials, is continuous at every point on its domain. So as long as you find the domain of the rational function, then you can say that's where it's continuous. So now that we know that, let's look at this example and discuss where f is continuous. In other words, write the interval where f is continuous. So A, we're going to start with a polynomial. Let's make it really easy. Let's do x squared, because it will be easy to graph, and C, it's a parabola. It's continuous. You can trace the graph without lifting up the pen, or we can just say it's polynomial. It's polynomial. Quadratic functions are polynomials, as well as linear and cubic and so on. Polynomials, so continuous everywhere, from negative infinity to infinity. B. Now we're going to do a rational function, make it very easy so we can graph it. You can make a table here. So this rational function, we call it hyperbola, has two parts. And we can see we have a big jump at 0 because when x equals 0, 1 divided by 0 is undefined. So where is it continuous? Everywhere except at 0. So it's continuous. We can write it as a set everywhere except 0. We can say from negative infinity to 0 and then from 0 to infinity if you want to write interval notation. C. Now another rational function, but this one is special. Just because it's a rational function doesn't mean the denominator is always equal to 0, because you can see, note, that x squared plus 1 is always positive for every x, right? For every x, because when you square a number and add 1, you always get positive. Then we can say this function is continuous everywhere, because the denominator never becomes 0. C. Oh, that was C. So now we have D f of x equals square root of 3 minus x. Now this is a rational function. So the rational function has a certain domain, which we need to write down first. What's happening at 3? If x equals 3, square root of 0 is 0. So 0 is in the domain. But we need to make sure what's under the square root is always greater or equal than 0. So we solve this inequality, we have x less or equal than 0. So we can say the domain is all x less or equal than 3. Or if you want to write it as an interval, that will be from negative infinity to 3, including the 3. So the graph looks like this. So it's opening to the left. And so let's explore the limit of the function for x approaching 3 from the left, because that's where it's defined, for smaller values than 3. Well, that is, substitute directly, square root of 3 minus 3, and it's 0. So the limit exists, and it's equal to, let's write down what is f of 3. F of 3 is 0, so these two are equal. We have the three conditions. For continuity, so we can say f is continuous on its domain from negative infinity to 3. And this concludes the video.